Today we're diving into the Kafka schema. What exactly is a schema in the context of Kafka? Schemas ensure compatibility between the producer and consumer. By defining the structure, they prevent mismatch expectations of the data being sent. This makes the communication between systems much smoother and less prone to errors. There are a few different types of schema you commonly encounter. Avro. This is a compact binary format that is great for data serialization. It's efficient in terms of storage and transmission. JSON Schema. This format is human readable and widely adopted, making it easy to understand and debug. Protobuf, known for its efficiency and cross-platform support. Protobuf is also binary, but offers some additional features compared to Avro. Now let's take a look at schema evolution. This is a reference slide, and we won't go into the details just yet. The idea here is to give you a quick overview of the compatibility types that come into play as schema evolve over time. Schema can change, and when they do, they may not always be backward compatible. This is where compatibility types come in. These compatibility rules help ensure that producers and consumers can continue to work with each other smoothly. In a moment, I walk you through each of these compatibility types, so don't worry about the specifics yet. Just know that each type defines how changes to a schema can affect the systems using it, whether that's allowing consumers to handle older versions or ensuring producers can send data that older consumers can still read. First, let's look at backward compatibility. According to the table, backward compatibility allows changes like deleting fields or adding optional fields, and it checks against the last version of the schema. It's important to note that consumers should upgrade first. Let's walk through an example of backward compatibility. Suppose we have a schema. Let's call this schema V1. The producer uses V1 to produce messages, and the consumer reads these messages using the same version. Now imagine we publish schema V2, where we add an optional field. The consumer still on V1 is able to read the messages produced with V2 because of backward compatibility. Next, let's look at backward transitive compatibility. In the table, we see that this type allows deleting fields or adding optional fields, and it checks against all previous versions of the schema, ensuring compatibility throughout the entire schema evolution. This means the consumer can read messages from any prior schema version. In backward transitive compatibility, we start with schema V1, then move to schema V2, which adds an optional field, and eventually schema V3, which removes a field. Even though the consumer is upgraded to use V3, it can still read messages produced with schema V1 thanks to backward transitive compatibility. Now let's move on to forward compatibility. The table shows that this type allows adding fields or deleting optional fields, and it checks against the last version of the schema. This means the producer can safely upgrade first, and the consumer will still be able to read the data produced by the new schema version. Let's now look at forward compatibility. If schema V1 is already in use by the producer and messages are being consumed with V1, we can publish schema V2. This time we remove an optional field, but the consumer still using V1 can still read the messages because of forward compatibility. Next up, we have forward transitive compatibility. According to the table, this type also allows adding fields or deleting optional fields, but it checks against all previous versions of the schema. This ensures that even consumers using older schema versions can still read the data from the latest version. With forward transitive compatibility, things get a bit more flexible. If schema V1 is used by the producer and schema V2 and V3 are subsequently published, the consumers using V1 can still read the data from schema V3. That's the beauty of forward transitive compatibility. Now let's look at full compatibility. The table indicates that this type allows both adding and deleting optional fields, and it checks against the last version of the schema. This ensures both producers and consumers can read data from any schema version, making the schema evolution process more flexible. Full compatibility takes it a step further. We can have multiple versions, V1, V2, and V3, and no matter what version the producer and consumers are using, they will be able to read and write the data seamlessly. Both the producer and consumer are flexible enough to handle any schema version. Lastly, let's discuss non-compatibility. In this case, schema changes can break compatibility. The table tells us that there are no compatibility checks, which means all changes are accepted, and consumer or producers might fail unless they are manually adjusted.